spheres having charges of 2 into 10 to the power minus 7 coulomb and 3 into 10 to the power minus 7 coulomb placed at 30 centimeter apart in the air. So here we have to find out force between two small charged spheres. So we have to find out electrostatic force. Now the expression for electrostatic force is given by Coulomb's law, which states that the electric force between two charged particles acts between the line connecting them, and it is inversely proportional to the distance separating them, and it is directly proportional to the product of those two charges. And also the same charge repel each other, and opposite charges attract each other. Now this can be summarized in a mathematical equation like this. Now Fe equals to K times Q1 Q2 divided by R square, where Q1 and Q2 are the magnitude of the charges, R is the distance of separation, and K is the constant, and for air it is 9 into 10 to the power 9 coulomb square per Newton meter square. Now here in this question we have been given the value of those two charges and the distance separating them. So we can easily substitute these values in the equation, and then we can find out what is the force. So substituting these values, we get force as equal to 6 into 10 to the power minus 3 Newton. Now since we have been given the charges that are both positive, so we can say that since charges are of same sign, that is positive sign, so that the force will be repulsive in nature. Thank you. The question says that the electrostatic force on a small charge sphere of charge 0.4 microcoulomb due to another small sphere of charge minus 0.8 microcoulomb in air is 0.2 Newton. Now what is the distance between these two spheres, and what is the force on the second sphere due to the first? So here again, this is the force between two charged particles governed by Coulomb's law that we saw in the previous lecture, that says that force is equals to K times Q1 Q2 divided by R square, where Q1 and Q2 are the magnitude of charges and R is the distance of separation between them. And opposite charges attract each other and like charges repel each other. Now here we have been given two opposite charges, so the force will be attractive in nature. We have been given the magnitude of force between them, that is 0.2 Newton, and we have been also given the value of Q1 and Q2, that is the magnitude of charge on those small spheres, that is 0.4 microcoulomb and minus 0.8 microcoulomb. So we have to find out distance of separation, that is R in between them. So here F is given, K we all know that its value is constant, and for air it is 9 into 10 to the power 9. Now Q1 and Q2 is also given, and R we have to find out. So we can, after substituting this in the given equation, we get the value of R as 12 centimeter. Thank you. The question says that check the ratio KE square by GMEMP is dimensionless. Look up the table of physical constants and determine the value of this ratio. What does this ratio signify? So here in question, the scenario is of two particles, namely electron and proton, and this ratio represents the ratio of the electrostatic force to that of the gravitational force. So we know the expression of electrostatic force, that is F, if we represent it by Fe, that would be equal to K times charge on electron, and it is represented by E, multiplied with charge of proton, again it is E, divided by distance of separation, that is R square. Now if we represent the distance of separation by R, then it would be K E square by R square. Now similarly, we can write the expression for gravitational force like this. Fg would be equal to G, that is gravitational constant, times mass of electron times mass of proton divided by R square. Now if we find out the ratio, that is Fe by Fg, that would be equal to this given quantity, that is Ke square by G, mass of electron times mass of proton. So we have to find out this ratio, and we have to determine the value of this ratio, and we have to say what does this signify. Now we know already that what does this signify. The ratio signifies the ratio of electrostatic force to that of the gravitational force, and if we find the value of it, then we can find by how much quantity electrostatic force is higher or lower than that of the gravitational force. So here we know that K is the Coulomb's constant, that is given by 8.988 into 10 to the power 9 meters square per coulomb square. Similarly, charge of electron, we know the value, and we have to take this value from the table. And G, the value of G is also known, the mass of electron and mass of proton is also known. So substituting these values in this expression, we will get the value of K E square by G MEMP equals to 2.27 into 10 to the power 39. Now this ratio represents the relative strength between electrostatic and the gravitational force, and we see here that force of electrostatics is 2.27 into 10 to the power 39 times that of the gravitational force. That is, electrostatic force is much higher than that of the gravitational force, and it is higher by the order of magnitude this much. Thank you. The question says that explain the meaning of the statement electric charge of a body is quantized. Why can one ignore quantization of electric charge when dealing with the macroscopic, that is large scale charges? So here quantized means discrete, and in terms of electric charges, quantized means it is integral multiple of the smallest or the elementary charge unit, and that elementary charge unit is charge of proton or charge of electron represented by minus e. So mathematically we can represent the phenomena of the electric charge of a body is quantized as Q equals to n times C, where n is the integer. So if the body is having a net negative charge, then it would be in minus multiple of whole number of E, and if it is in positive, then n would be positive. Now the question is, why is charge quantized? A charge on any body is by the virtue of transfer of electrons and protons, and they transfer in whole numbers. So, and this is the fundamental unit of charge, that is E. Now they both carry equal charges, thus the charge always remains the integral multiple of E. Charge on a body is always the integral multiple of E. Now the second part of this question is, why can one ignore quantization of electric charge when dealing with macroscopic, that large scale charges? So the elementary charge is really small as compared to typical macroscopic charges. For example, if we have charge of 1 microcoulomb on any body, then it would be composed of 6.25 into 10 to the power 12 electrons. Now this number of electrons is quite massive, and therefore the charge always appears continuous for macroscopic charges, and the quantization can be ignored for macroscopic phenomena. Thank you. The question says that when a glass rod is rubbed with a silk cloth, charges appear on both. A similar phenomenon is observed with many other pair of bodies. Explain how this observation is consistent with the law of conservation of charge. So the law of conservation of charge says that in an isolated and closed system, total charge remains constant. So let us understand the physical significance of it. Let us assume that there are two bodies, A and B. Body A and B, initially they are both neutral, and after rubbing, body 2 electrons transferred from body A to B. There is exchange of 2 electrons. Now body B will acquire more electrons, so it will be minus 2e net charge, and on body A, since it is deficient of 2 electrons, so it will be having plus 2e charge. So initially they both were neutral, and finally total charge in this system is equals to 0. So this is what law of conservation of charge says, that in an isolated and closed system, total charge remains constant. So initially we saw that glass rod and the silk cloth are both neutral, and after rubbing, just like in this A and B body, we saw that glass becomes positively charged and this silk cloth becomes negatively charged. Now which of the bodies will give up electrons depends upon the triboelectric series. So this is the triboelectric series. So in this series, the glass, we see that it has tendency to give up electrons to the highest, and below comes the silk. That is, if we rub glass and silk together, then glass has higher tendency to lose electrons than silk. So obviously when we rub these two, then glass will become positively charged and the silk will become negatively charged. Now since these two bodies are isolated and the system is closed in the sense that there is no any foreign electrons that is coming to the system of glass and silk. The question says that 4-point charges QA, that is of 2 microcoulomb, QB of -5 microcoulomb, QC of 2 microcoulomb, QD of -5 microcoulomb are located at the corners of a square ABCD of side 10 centimeter. What is the force on charge 1 microcoulomb placed at the center of the square? So there are 4 charged particles, namely QA, QB, QC and QD, and they all are arranged in a form of a square. Now if we assume that the square has 4 vertices of namely ABCD, and the particles are arranged at the corners ABCD, namely QA as 2 microcoulomb, QB as -5 microcoulomb, QC as 2 microcoulomb and QD as -5 microcoulomb. We have to find out what is the net force on charge 1 microcoulomb placed at the center of the square. Now let us assume that the center of the square is O, where 1 microcoulomb of charge is there. Now we have to find out what is the net force on this 1 microcoulomb charge. So we know that electrostatic force is given by Coulomb's law, and mathematically it is expressed as force equals to K times QA QB divided by R square, where QA and QB are the charge of the particles A and B, and Coulomb's law also states that the force between these two particles would be along the line joining these two particles. And it also says that like charges repel each other, that is, if the charges have same sign they will repel, and if the charges have opposite sign then they will attract each other, and R is the distance of separation between them. So individually we have to calculate the forces acting by all those 4 particles on this charge at the center. So we see that force AO would be equal to, after applying this formula we will get a force of 3.6 Newton. Now since the charge at the center O and QA have both same sign, that is they both are positive, then the force will be repulsive in nature. Similarly with QC and O, it will be 3.6 Newton because magnitude of the charges are same, and again it will be repulsive. So, and since this is a straight line AOC, so they both will cancel out each other. Similarly we can see about this diagonal, that is DOB. Now force OB would be attractive in nature because this is positive in sign and this is negative in sign, and the magnitude would be given by 9 Newton after applying this formula. And similarly FOD would be equal to 9 Newton as well. Now they both will be attractive and they both will attract this 1 microcoulomb charge equally in opposite directions, so again they will cancel out each other. Now we saw that there are opposite forces and they are of equal magnitude and they all are cancelling out each other, so net force on this 1 coulomb charge particle would be 0. Thank you. The question says that an electrostatic field line is a continuous curve, that is, the field line cannot have certain breaks. Why not? So let us first understand a few properties of the electrostatic field lines. The first is field lines start from positive charge and end at the negative charge. That is, the field lines start at positive charge and they will end at negative charge. The origin of the field lines are from the positive charge and they end at negative charge. The second is, in a charge-free space, the electric field lines can be taken to be continuous curve without any breaks. That is, the electric field lines are continuous curves without any breaks in a charge-free space. Now, the question asked that an electrostatic field line is a continuous curve, that is, the field lines cannot have certain breaks. Why not? So this continuity arises because electric field is a vector field with a defined magnitude and direction at every point in space. That is, there is no any space where we can assume like there was a field line and there is a gap and the field line is continuing like that. So this is not practically or physically possible because charges cannot disappear. The force cannot disappear on a charge over here if the charge particle is over here, and it can't disappear and reappear over here. So a break in the field would imply an indefined or infinite electric field, which is physically impossible. So that is the reason why electric field lines are continuous curves without any breaks. Now the second question said that explain why two field lines never cross each other at any point. Now the third property of field lines says that two field lines can never cross each other. If they do, at the point of intersection, there would be ambiguity in the direction which rejects the concept of field line. We know that each electric field line has a definite direction. Now let us assume that this is a field line and this is another field line. We are assuming that the field line are crossing. Now at this point of intersection, this field line is saying that I have a direction in this way, and this field line is saying that I have a direction this way. Now at this point we have got two directions, which is practically impossible. So the field lines can never cross each other at any point. The question says that 2-point charges QA, that is of 3 microcoulomb, and QB is of -3 microcoulomb, are located 20 centimeter apart in vacuum. What is the electric field at midpoint O of the line AB joining these two charges? And if a negative test charge of magnitude 1.5 into 10 to the power -9 coulomb is placed at this point, that is in the middle point, what is the force experienced by this test charge? So this is the pictorial representation of the question. So there are 2 points A and B on which QA and QB charges are put respectively, and they are 20 centimeter apart. Now the scenario is there is a test charge in the middle of the line joining these two charges, that is AB, and the test charge has a magnitude of 1.5 into 10 to the power -9 coulomb. Now we have to find out what is the electric field at midpoint of the line joining AB. So electric field is given by K times Q divided by R square, and the direction of electric field is from positive charge to the negative charge. So the direction of electric field would be from charge A to charge B. Now we know that K is the Coulomb's constant, that is 8.99 into 10 to the power 9 Newton meter square per Coulomb square. So after substituting these values, we will get the magnitude of electric field. Now electric field, the contribution of electric field at the midpoint would be because of charge A and as well as charge B. So we will find out electric field due to charge A and due to charge B as well, and we all know that electric field, total electric field would be the vector summation of electric field due to individual charges. Now since these two are in the straight line, so we can simply add it, as the direction of electric field is going to be same from A to B in both the due to both the charges. So EA upon calculation is 2.697 into 10 to the power 9 Newton per Coulomb. Similarly, EB is 2.697 into 10 to the power 6 Newton per Coulomb, and total electric field would be equal to 5.394 into 10 to the power -6 Newton per Coulomb. Now direction of electric field would be from A to B. Now the calculation of force on the test charge. So F test can be given as the magnitude of charge times E total. Now since the test charge is negative, so its direction would be from B to A. The direction of force would be from B to A, because positive charges attract the negative charge and negative charge repels the negative charge. So B is negatively charged and A is positively charged. So the magnitude of force would be equal to 8.091 into 10 to the power -3 Newton, and it would be directed from B to A. Thank you. The question says that a system of two charges QA and QB, that is of magnitude 2.5 into 10 to the power -7 coulomb and -2.5 into 10 to the power -7 coulomb, located at points A 00 -15 centimeter and B 00 plus 15 centimeter respectively. What are the total charge and the electric dipole moment of the system? So we can clearly see that the charges are of equal magnitude and opposite sign, separated by a distance of 30 centimeter from 001 minus 15 centimeter to 00 plus 15 centimeter on the z-axis. So this is a case of electric dipole. Now we have to find out what is the total charge and what is the electric dipole moment of this system. So this is the pictorial representation of the question that is given. On the negative direction, on the negative side of the z-axis, there is a point at 15 centimeter from the origin, that is A, where the charge of 2.5 into 10 to the power minus 7 coulomb is there, and on the right hand side we have got a charge of minus 2.5 into 10 to the power minus 7 coulomb, that is on point B. So we know that electric dipole is defined as charge multiplied with the distance separating them. So the charge is 2.5 into 10 to the power minus 7 coulomb multiplied with distance, that is 15 centimeter plus 15 centimeter would be 0.3 meter, and thus we get the electric dipole of 7.5 into 10 to the power minus 8 coulomb meter. Now since this is an electric dipole, the equal and opposite magnitude of charge is there, so the total charge would be equal to 0. And the direction of electric dipole is from negative charge to positive, so it would be from point B to A. The question says that an electric dipole with a dipole moment of 4 into 10 to the power minus 9 coulomb meter is aligned at 30 degree with the direction of uniform electric field of magnitude 5 into 10 to the power 4 Newton per coulomb. Calculate the magnitude of torque acting on the dipole. So the question talks about interaction of an electric dipole in an uniform electric field. Now since electric dipole is composed of positive and negative charge of equal magnitude, and if they are put in electric field, then they will experience force, and thus net torque will be produced. So this is the pictorial representation of this question. In the thin blue line from left to right, we see that uniform electric field is there of magnitude 5 into 10 to the power 4 Newton per coulomb, and this diagram that we see, that is of the electric dipole. At point A there is a negative charge, and at point B there is a positive charge, and we know that the negative charge experiences force on the opposite direction of the electric field, and the positive charge experiences force in the direction of electric field. Now taking component perpendicular to the electric dipole axis, we will get EQ sine 30 degree on both the sides for both the charge. Now calculating the net torque, we will see that it is equals to QD times E sine 30 degree, where E is the magnitude of electric field, that is uniform, D is the distance of separation between the charges, and Q is the magnitude of charge. So this is going to be the magnitude of torque, which can be represented by P E sine theta, where P is the electric dipole moment. Now QD represents the electric dipole moment, so we can write torque as P E sine theta. Now using the values that has been given in the question, we get the torque of 10 raised to the power minus 4 Newton meter acting on the electric dipole presented in the uniform electric field. Thank you. The question says that a polythene piece rubbed with wool is found to have a negative charge of 3 into 10 to the power minus 7 coulomb. Estimate the number of electrons transferred from which to which. Is there a transfer of mass from wool to polythene? So we see that when polythene piece was rubbed with wool, it gained negative charge, that is the electron from wool transferred to the polythene piece. So this part of the question is estimate the number of electrons transferred from which to which. So from which to which, we already know that if polythene becomes negatively charged, then the wool must lose those electrons to give polythene the extra electrons, thus it became negatively charged with the magnitude of 3 into 10 to the power minus 7 coulomb. So we have to find out number of electrons. We know that charges are quantized, so we can express charges with an integral multiple of the elementary charge particles, and elementary charge is 1.6 into 10 to the power minus 19 coulomb, and here we are dealing with the negative charge, so the transfer of electrons is from wool to polythene. Now if we have to find out number of electrons transferred, then we can divide the total charge transferred divided by the elementary charge, then we will get the total number of electrons transferred, and thus it's of value 1.88 into 10 to the power 12 electrons. Now we also have to find out, is there any transfer of mass from wool to polythene? So this number of electron has been transferred, so there must have been some mass transfer also taken place. Now if we find out the mass that has been transferred, we get the value of 1.71 into 10 to the power minus 18 kg. Hello everyone. The question says that what is the force between two small charged spheres having charges of 2 into 10 raised to the power minus 7 coulomb and 3 into 10 raised to the power minus 7 particle of magnitude 2 microcoulomb inside the center of a cube that is of side 9 centimeter. Now what would be the electric flux through the surface? So we can assume that this is the Gaussian surface of cube of side 9 centimeter. Now we can apply Gauss law as here. Gauss law states that total flux outward or inward through the Gaussian surface would be equal to total charge enclosed within the surface divided by epsilon naught. Now we can use this formula straightforward to find out the flux outward of this surface, outward of this Gaussian surface. So we can get the expression, we can substitute the values of the expression in this expression, and we will get the value of 2.26 into 10 to the power 5 Newton meter square per coulomb. Thank you. The question says that a point charge causes an electric flux of minus 1.0 into 10 to the power 3 Newton meter square per coulomb to pass through the spherical Gaussian surface of 10 centimeter radius centered on the charge. So here electric flux is given, the value of electric flux is given, and it is passing through the spherical Gaussian surface of 10 centimeter of radius. Now we can assume it as phi 1. Now if the radius of the Gaussian surface were doubled, how much flux would pass through the surface? And the second question is, what is the value of point charge? So here we can apply Gauss law to find out the point charge. We know that Gauss law states that total flux through the Gaussian surface would be equal to Q enclosed within the surface divided by epsilon naught. Now here electric flux is given and we are being asked about the Q enclosed, that is charge enclosed within the Gaussian surface. So we can get the value of Q enclosed by multiplying this flux with epsilon naught. Now the first question said that if the radius of the Gaussian surface were doubled, how much flux would pass through the surface? Now let us assume that the first case where radius was r, the flux would be equal to phi 1, and the second case where r is doubled would be equal to phi 2. So here we see that in both this Gaussian surface the total charge enclosed doesn't change, so the flux would also not change. So that's why we can say that the flux remains same even if the radius is doubled. And the charge enclosed, as I told you earlier, we can find it using this formula. Charge enclosed would be minus 8.85 nanocoulomb. Thank you. The question says that a conducting sphere of radius 10 cm has an unknown charge. If the electric field 20 cm from the center of the sphere is 1.5 into 10 to the power 3 Newton per coulomb, points radially inwards, what is the net charge of the sphere? So the question is saying that there is a conducting sphere of radius 10 cm and it has some charge due to which there is an electric field 20 cm away from the center, and the value of electric field is 1.5 into 10 to the power 3 Newton per coulomb, and this electric field is towards the sphere. So since this electric field is directed towards the sphere, so we can say that there is a negative charge inside the sphere. Now we have to find out what is the net charge on the sphere. So by Gauss law we know that for a spherical charge distribution, electric flux would be equal to Q enclosed divided by epsilon naught. Here electric flux is the multiple of electric field multiplied with the surface area of the surface enclosing this charge. Now for a sphere, the surface area of a sphere would be 4 pi r square. Now E dot 4 pi r square would be equal to Q enclosed divided by epsilon naught. Q enclosed is the charge inside the Gaussian surface. Now we can find out the expression for Q enclosed as here as E dot 4 pi r square multiplied by epsilon naught. Here E would be equal to 1.5 10 to the power 3 Newton per coulomb, and this is the surface area of the sphere of radius 20 cm, and this is epsilon naught. Now we know that the electric field is pointed towards the sphere, so there is a negative charge inside the sphere. Thus the charge would be minus 6.67 nanocoulomb. Thank you. The question says that a uniformly charged conducting sphere of 2.4 meter diameter has a surface charge density of 80 microcoulomb per meter square. Find the charge on the sphere. And the second question is, what is the total electric flux leaving the surface of the sphere? So by definition of surface charge density, we know that surface charge density sigma is defined as total charge divided by surface area. Now using this expression, we can find out the value of total charge on the sphere, as Q would be equal to sigma times A. Now A for the sphere would be equal to 4 pi r square. So the value of charge on the sphere would be 1.44 microcoulomb, 1.448 microcoulomb. Now the second question was, what is the total electric flux leaving the surface of the sphere? Now we can assume a Gaussian surface around this sphere, and as per Gauss law, flux through the Gaussian surface would be equal to total charge enclosed by the Gaussian surface divided by epsilon naught. Now since this Gaussian surface would be enclosing this charge, this magnitude of charge Q, 1.448 microcoulomb, and we can use this expression now for finding the flux. So flux would be equal to 1.64 into 10 to the power 8 Newton meter square per coulomb. Here we see that while assuming Gaussian surface, we can assume Gaussian surface that covers this sphere of any radius. So just the sphere should be inside the Gaussian surface. The question says that an infinite line charge produces a field of 9 into 10 to the power 4 Newton per coulomb at a distance of 2 centimeter. Calculate the linear charge density. So we have to calculate the linear charge density given that the infinite line charge produces a field of 9.9 into 10 to the power 4 Newton per coulomb. So let us assume that this is the infinite charge line, and at a distance of 2 centimeter away from this line charge, the electric field is of this much magnitude is produced. So what is the linear charge density, or lambda? Lambda is defined as total charge divided by length of the line. So we have to find out this value of lambda. Now we have an expression for electric field due to an infinite line charge, and that says that E is equals to lambda by 2 pi epsilon naught r. Now we can find out lambda using this expression, and that would be given by E into 2 pi epsilon naught r. And using this expression, we have got the value of as lambda as 0.1 microcoulomb per meter. Now how this expression came, let's understand it a little bit deeper. Now let's assume that this is the line charge. In this question it is of positive charge, so we can assume it as a positive charge. Let us assume that there is a point r at a distance of r away from this line charge. Now we have to find out, either we have to find out Q, that is the charge on this line, or we have to find out electric field, or we have to find out flux. Now we can use Gauss law over here. Now we can assume a Gaussian surface, a cylindrical Gaussian surface over here of radius r. Now electric flux outward of this upper and lower face of the cylinder would be 0, because electric field would be perpendicular. So it would be 0 from this face and this face as well. So the only electric field contribution would be from the curved surface area. And from the Gauss law, we know that flux is given by Q enclosed divided by epsilon naught. Now flux is defined as E multiplied by surface area. So E dot the curved surface area of cylinder is equals to 2 pi r multiplied by length, or the height. This is the length. That would be equal to Q enclosed. Now Q enclosed would be given by lambda times L. Lambda is the linear charge density multiplied by length L divided by epsilon naught. Now here we see that the expression of E would become L would cancel out each other. Now lambda divided by 2 pi r epsilon naught. Now this is the same expression we used in the upper question to solve the question. So it comes from here as per the Gauss law. Thank you. The question says that two large thin metal plates are parallel and close to each other. On their inner faces, the plates have surface charge densities of opposite sign and of magnitude 17 times 10 raised to the power minus 22 coulomb per meter square. So the configuration is like this. There are two plates. I have symbolized them as red and the black one. They are carrying opposite charges of charge density sigma equals to 17 times 10 to the power minus 22 coulomb per meter square. We have to find out what is the electric field in the outer region of the first plate, that is this region, outer region of the second plate, that is this region, and between the plates, that is this region. Now we can leverage the Gauss law in this, which states that net flux from any surface is equals to Q enclosed, that is the charge enclosed in that surface, divided by epsilon naught. Now flux is given as E dot ds, or the dot product of electric field and the area vector. Now the geometry in subject is of thin metal plates parallel to each other. Now we can assume it as like this. Now we can assume the Gaussian surface to be of a parallelopiped like this one in the green box that we can see. Now the electric field due to this thin metal plate would be parallel to these all four faces, this one, this one, this one, and this one. So they won't contribute to the electric flux, because we know that dot product angle between them would be 90 degrees, so it would result out to be 0. Now the flux due to this number 1 phase and number 2 phase will be counted, and they both will add up to 2EA. Now A would be the area enclosed of this surface. Now sigma A would be the charge enclosed in this parallelopiped. Now this flux, this is quantity is flux, and this is the charge enclosed divided by epsilon naught. Now from this we can know that E is equals to sigma by 2 epsilon naught. So for this region of our interest, that is away from both of the plates and near the first plate, we can make a Gaussian surface that would enclose both the charges, and thus they both are having equal and opposite surface charge density. And since Gaussian surface is enclosing both the plates, so the net charge would be 0. So electric flux due to both these metal plates at point A would be equal to 0. Similarly at B it would be equal to 0, and at C it would add up because they both are of opposite charge, and Gaussian surface of this would result EA. Gaussian surface of this positive plate would result the electric field as sigma by 2 epsilon naught. Similarly by the negative plate it would result out to be sigma by 2 epsilon naught, and they both will be of same direction, from away from the positive charge and towards the negative charge, like this one. Now they both will add up. Since the angle between them is 0, so they both will add up, and the vector addition would be sigma by epsilon naught, and this would give us 1.92 into 10 to the power minus 11 Newton per Coulomb. Thank you.